So hello everyone, this is lecture 10 for the electricity and magnetism. In the last lecture we have studied about the electric dipoles and today we'll study what is polarization. So let's see, polarization is defined in the dielectric materials. And what is the dielectric materials? Where the electrons are very tightly bound, means they are not free to move. So let's see, we have some atom of a dielectric material and this is uniformly charged, means you can see this electron cloud and the nucleus. Now when you apply some electric field on it, then this negative charge will displace to this side and positive will displace to this side, and this is something like this, and this situation we call polarization, and this is polarized atom. So this kind of dielectric material you have and single atom we have taken, and this is defined as polarized atom. And the polarization of this single atom is defined as, means the dipole moment can be written as q into d, where this d is distance between these displaced charge, okay, plus and the minus, and qd will give you your dipole moment, and that is equal to alpha e, where e is the electric field applied and alpha is the atomic polarizability. So that's how you define polarization or the dipole moment for a single atom. Now let's see, if we apply the complete electric field to the whole material, then what happens? Let's say first the polarization is uniform, and let me define you what is the polarization in the complete material. It is the dipole moment per unit volume. Okay, so that's how we define this. Now if it is uniform polarization, means P is constant, that is dipole moment per unit volume is constant. So let's see, we have applied the electric field, then all the negative charge will displace this side and positive will displace this side. And inside we have this kind of thing. So now see that we have some bound charges inside, means the charges inside the material is bound charge, means volume bound charge, and the charges at the surface is called the surface bound charge, and this complete charges is called the bound charges. So we have two kind of bound charges, that is volume bound charge that is lying inside this material, and the surface bound charges that is lying on the surface. So see, when the polarization is uniform, means P is constant, then this net bound charge inside the volume will be 0, because all the positive equal to negative. Except these surface charges, we have only these bound charges. Then these volume bound charge which is lying inside, that will be 0 always for the uniform polarization. So when the polarization is uniform, this density inside, means volume bound charge, will be 0, but the surface bound charge is not equal to 0, because we have some net charge negative here and net charge positive here. So I hope you understand this thing. Let's move for the non-uniform polarization. Now if this polarization is not uniform, then what happens? Means P is not constant, then we will have definitely some volume charge density also, means volume bound charge also, means both will be non-zero. And these are the formula you must remember, that to find the volume bound charge density is equal to minus divergence of polarization, and to found the surface bound charge density, it will be, these are densities, okay, so it will be p dot n cap, where this n cap is the direction of the surface on which you are finding the surface bound charge density, and p is the polarization of the material. So you must remember these two formulas. We will see how we apply them. Now if you know these densities, surface charge, surface bound charge density and the volume bound charge density, then you can find the total bound charge on the surface and the volume. So for the volume bound charge, it will be, means density multiply the volume element, and again for the surface bound charge will be density multiply the area element, that will give you total charge on the surface and the bound charge on the inside the volume. And see, these sum will always remain 0. You can see, if I make a Gaussian surface around this, the net charge will always remain 0. So these two charges must be equal, means sum of these must be equal to 0. That means q rho b equal to minus q sigma b. So that's why. So you must remember these properties, very useful. Now the field due to bound charges. So let's see, we can define potential due to bound charges same as we define for a single charge, means sigma b dA will give us the charge, and divided by 4 pi naught r will give you potential, and same for the volume bound charge. So if we can define potential in the same way, then we can define the electric field using the Gauss law again, that we can take any surface inside, then we'll calculate the total charge inside, and we can apply the Gauss law again here also. So E dot dA will give you Q enclosed divided by epsilon naught, and this is bound enclosed charge, means we are detailing, means we are discussing only about the bound charges here. So electric field due to bound charges. So make a surface, and inside that charge, that will be here, divided by epsilon naught. So total bound charge inside that surface. And remember, outside the polarized material, the electric field due to bound charges will always 0, because total charge if you make some sphere something like this, any surface, then inside total charge is 0. That's why the electric field outside the polarized material will always be 0 due to bound charges. Always remember, we are discussing bound charges. Let's take some examples. A sphere of radius r carries a polarization p kr. So see, this polarization is non-uniform because depending on the r vector, where k is some constant, r is a vector from the center. Now we need to find the surface bound charge density, volume bound charge density, and total surface charge, and the total volume charge. And then we need to find the total charge, and then find field due to bound charge inside and the outside the sphere. So we need to use these formulas to find the densities. So let's see, this is your sphere and this is some vector. Now p polarization defined as kr, and see in the spherical polar coordinates, this r means in the Cartesian r can be written as x cap, y cap, z cap, and we know this vector in the spherical coordinates is kr r cap. So now we have polarization. So bound charge, volume bound charge density is nothing but divergence of p. So just take the divergence of this. In the spherical coordinates, it is 1 upon r square del by del r square multiplied by p, that is kr r cap. So r cap will be negative because r cap will give you 1. Now take the differentiation, it will give you minus 3k. Same now, if you have the density, you can find the total volume charge, that is rho v d tau. So rho v is this minus 3k, and d tau is volume element. So volume element is, for the sphere, it is 4 pi r square dr. So integrate this will give you r cube by 3, and 3 will cancel out. Then it will be r limit, that is minus 4 pi kr cube. So this will be your total volume bound charge inside. Now let's see the surface bound charge. See, there is only one surface, that is outside. So we need to put r equal to capital R, and let's find first the charge density, that is p dot n cap, and n cap is the direction perpendicular to this surface, and p is kr r cap because it was small r, but we have surface only on the capital R, that's why I put it here kr. Now this will give you kr. This is the total surface bound charge, means this is total surface bound charge density. Now to find the total charge, it is the multiply with area element, and see, surface is only this surface, so multiply with 4 pi capital R square. So 4 pi r square kr will give you 4 pi k r cube. And now see that the surface bound charge is equal to the total bound charge inside the volume, and that is minus of this, so that total charge can be become 0. So both are equal, so total bound charge will be 0. Now if we talk about the electric field, then r greater than r means outside this sphere, that electric field will be 0 because total net charge is 0. Using Gauss law we can say that. But to find the electric field inside some point at this point, so you need to find the total charge, bound charge inside this sphere. So here we need to use the property, means we know what is volume charge density, we already find this for the bound charges, that is this minus 3k. So E dot multiply 4 pi r square, that is E ds equal to total charges rho and the volume element, means we are using this formula. So this will give us minus 3k, and r cube by 3 will give you, 3 will cancel out, and just put the limit, and this r square will cancel out, will give you single r. So just electric field will be minus kr by epsilon naught r cap. Okay, so that's how you can find the electric field. Now there is another example. Thick polarized dielectric sphere. So this is dielectric sphere, and thick means there is some hollow space, and this is thick, something, some width have a to b. The inner radius is a, outer radius is b, and there is some smaller sphere we have taken, that is r. We will discuss about that. Just remember that is a polar dielectric sphere whose inner radius is a and outer radius is b, and this is, and this is inside, it is polarized, and the polarization is given by k by r cap. So again this polarization is non-uniform. So to find the volume bound charge inside this system, that will be minus divergence of p. So again use the spherical polar coordinates, that is 1 upon r square del by del r square k by r. This will give you minus k by r square, that is your volume bound charge density. Now total bound charge, volume bound charge will be rho b d tau, and the volume element is again 4 pi r square dr. But see, limit will be a to b because only here we have this density. So a to b, this will give you total volume bound charge, that is minus 4 pi k b minus a. Now see, we have two surfaces this time. This one surface at r equal to a, and second surface at r equal to b. So we need to find the surface charge density for both these surfaces. For r equal to b, let's first find for this outer surface. Direction of this outer surface will be perpendicular outside. So let's say that is r cap because the spherical coordinates we are discussing, and this Polarization means it is P dot n cap. So polarization is given as K by R cap. So for this B surface, it will be K by B and R cap. So K by B R cap and dot R cap will give you 1. So it will be K by B. Now total surface charge on this B surface will be density multiplied by the surface area, that is 4 pi B square. So this will give you 4 pi KB. That is your surface bound charge for the B. Now to find for the A, we will do the same thing, but this time the area direction will be inside because this is outer the surface. And see, this polarization direction will be in the outer world. So it is K by R cap and that is minus R cap. So this will be K by B. Sorry, I put it here A. K by A R cap minus R cap. So that will give you minus K by A. And now total bound charge on the A surface will be minus 4 by K, because you will multiply with 4 pi A square here. So that's how you can find. So see, this total surface bound charge will be sum of this and this, and this is your volume bound charge. So this must be equal to sum of these. Let's see if it is equal or not. Let's take the sum of these two. This will give us 4 pi K B minus A, and that is same as we find for the volume bound charge. So that means total charge will be 0 again, and that is the property you must remember, because you can use it directly. You don't need to find the surface charge every time. You just take it as equal to minus of the total volume bound charge. Now let's find the electric field. So we have three reasons here. First reason is inside this, second reason is inside this, and third reason is outside. So outside electric field will be 0 because total net charge is 0. Inside this, total electric field will be 0 because net charge is 0. Now we need to find the electric field in this region. Let's say some sphere at radius r. So we need to find the total charge first. So total charge will be the surface charge on this A sphere, this A surface, and the second is the total volume bound charge between A to B. Sorry, A to R. It is A and this is R. So A to R, you need to find the volume bound charge. So let's see. R less than A is 0, no bound charge. R greater than B is 0 because total bound is charge 0. Now A to B, E into 4 pi R square using the Gauss law. So we need to multiply this area, E 4 pi R square, equal to 1 by epsilon naught, and the charge due to the A sphere, this inside one, that is we already find this value minus 4 pi Ka. Then A to R, we use the volume bound charge density and multiply the volume element 4 pi R square dr. And solving this, this will be this. Now this will be minus 4 pi plus 4 pi Ka will cancel out this. You will get only minus 4 pi Kr divided by epsilon naught. And now this 4 pi will cancel out and you will get only electric field as minus K by epsilon naught R cap. So this is your electric field inside the this A to B. Now see, there is another question. Now same we have to solve in the cylindrical polar coordinates. So polarization is given as 5z square plus 7z cap. So polarization is given in the cylindrical coordinates. Find all the bound charges. So again we will use the volume bound charge density, that is minus del dot P. So find the divergence of P in the in the cylindrical polar coordinates. So the formula we already know. This length is total 0 to L. So z is going from 0 to L. You must remember that. So del dot P is simply minus del by del z, 5z square plus 7. This will give you minus 10z. Now you have the volume bound charge density. So total bound charge will be rho B d tau. And now this is the volume element. So it will be dr d phi dz, and L is going from 0 to L because z is going from 0 to L. Radius is going from 0 to R, and this phi is going from 0 to 2 pi. So that is the thing, R phi z in the cylindrical polar coordinates. So minus tan z R dr d phi dz. D phi will give you 2 pi. Dr R will give you R square by 2, and dz will give you z, and that is L minus 0 L. So this will be, sorry, dz, you have z here, that will be z square by 2. So you need to put L square by 2 and minus 10. So this will be your total volume bound charge. Now you can directly find the surface bound charge easily, that is equal to plus 5 pi L square R square, because total charge must be 0. But let's find it if that value is same or not, plus 5 L square R square or not. So we have three surfaces here. First is this at L length, second surface is at L equal to 0, in Z equal to 0, and third surface is this curved surface. So let's find for each. So for Z equal to L first, we have surface bound charge density as R P dot n cap. Now polarization is this. So at Z equal to L, put L here, 5L square plus 7, and dot n cap is also in the Z cap direction. So it will give you Z cap 1. So it will be 5L square plus 7. Now for z equal to 0, this surface, the polarization is again in this direction, means it will be 7 z cap, but the surface direction is in this direction, minus n cap. So it will be minus z cap, so it will give you minus 7. Now for r equal to r, means for this curved surface, the direction of the polarization is again in z cap and the surface direction is perpendicular to it. So p dot n cap will always give you 0 here for this third surface. The total bound charge, means surface bound charge, will be this multiply the surface area, that is pi r square, and this multiply the surface area, that is pi r square. Now this minus 7 will cancel out. The remaining one will be 5 pi l square r square. So see, this is same as this but in the positive sign. So that's why you can calculate directly after this. So you just no need to do this. So this sum will, total charge will be 0 again. So that's how you can use, or I hope this is clear to you, what is the bound charges and how can we handle with them. So that's all for today. We'll meet you in the next lecture. Thank you everyone.